Um, so namaste, hello, and I'm in Japan, so this is how you would say hello, konnichiwa. I'm like Sundar said, I'm a researcher at the ACSL Kondo Laboratory in Keio University. It's one of the private universities in Japan. Before that, I did my master's and PhD in the University of Tokyo in the Nakamura Kondo Lab. And before that, I was in Culture campus. I did my bachelor's from the Department of Electronics and Communications Engineering. Um, yeah, so again, so today's talk, so what, yeah, what I do. So my research is mainly about machine learning, but rather than the core machine learning, it's more about applications. So my PhD and master's was usually done on how we can use machine learning for the Internet of Things, in a very specific type of machine learning called reinforcement learning, and it was mainly for how to manage resources in these small energy constrained devices. Uh, Now I'm doing some research on how we can use computer architecture insights to accelerate machine learning in computers, and also how we can use machine learning for quantum computing. Basically, quantum computing systems are very noisy, and how can we make sure that our computing systems are more tolerant to such kind of noise? So what this presentation is about, it's only a very, very, very brief introduction to linear algebra. I haven't made a very long presentation, given that maybe you would like to have some sort of discussion at the end, but depending on how we go, we can figure that out. But basically, this presentation is algebra, not at all exhaustive. I'm assuming you are already somewhat familiar with linear equations and what vectors are and what matrices are and what dot products are. Um, in my own experience, when we do these kinds of camps, one problem we have is we try to take in a lot at the same time and kind of like burn out or explode in our heads. So think of this more as an intuitive overview of the important concepts. And I will be focusing just until eigenvectors and eigenvalues. I had originally planned to go into much more stuff like QR factorization and singular value decomposition, but given the time and time limits and all that, I think I will just stop at the eigenvectors and eigenvalues for today. Um, Again, since we're talking linear algebra, there are matrices. I will have to use these references from the movie of Matrix. Um, so think of this as I'm just showing you links on how you can get more information rather than using this as an overall complete lecture to learn about linear algebra. So this is not about, this presentation is not about how to compute stuff, like how to do LU decomposition, how to do QR factorization, or any of these. For that, you have lots of textbooks, you have lots of resources on the internet, and obviously, like I said, it's not an exhaustive formal treatment. However, how you can make use of this is to think of it as a rough layout of how linear algebra pertains to machine learning in general. So rather to build intuition rather than skills. Ask very fundamental questions rather than try to solve complicated problems. More like, why are we doing this? What does it really mean versus how to do something? So when we say dot products, we all know how to do dot products, but what does it really mean? Why are we doing this? What kind of implications does it have? That's the kind of thing I would like to give in this lecture. It's okay if some of it is not very clear. There is still a lot of links in the slides so that you can follow on later. Mm. So basically what we will learn about today are what are matrices, what are vectors, what kind of rules govern this kind of their manipulations and their working in mathematical space, what they can represent, and how they're kind of applied in machine learning. So we have this very famous GIF, a meme, where they say that unfortunately no one can be told what the matrix is, but fortunately for us, we can totally say what the matrix is. In fact, it has been said 200, almost 300 years ago. And to summarize, matrix is simply just a bunch of numbers arranged in a rectangular formation. So, for example, let me change my. For example, this is a 2 by 3 matrix, which basically means it has 2 rows and 3 columns. This is a 2 by 2 matrix. It has 2 rows and 2 columns. The entries, the horizontal entries are called rows. The vertical entries are called columns. This is very fundamental. We have a 2 by 1 matrix. This has a very special name. It's also called a vector. And this is a 1 by 3 matrix. This is also called a vector. This is called a column vector, whereas this is called a row vector because this is only one column, and this is only one row. Very simple stuff. I will just use this. So like I said, vectors are matrices with a single column or single row, but for purposes of this presentation, we will assume when we say vectors, we are talking about column vectors. So vectors with columns, matrices with just one single column are called column vectors. You can have as many entries as possible. And similarly, if matrices have only one row, they're called row vectors. So why these matrices and vectors and what they really are? When I first started learning matrices and vectors, they were in my optional math class when I was in class 8 and 9. So didn't really understand what they were about. And we usually start with very abstract mathematical concept. And what you can think of them are like that as abstract mathematical concepts. It's like a language. They have very well-defined definitions and they have well-defined rules. And if you follow those definitions and rules, you can actually get some meaning out of them. So, for example, just a very fundamental example. We all know about the concept of number 2. 2 can represent 2 apples. 2 can represent 2 cats. And the same concept of 2 can even represent the flow of time. So if you have 0 seconds and you add 2 seconds, you get 2 seconds later. So similarly, you can use matrices and vectors to represent very meaningful stuff in machine learning and in other areas of engineering and maths and science. And that is how I think we should look at it. So matrices by themselves and vectors by themselves are abstract mathematical tools. And how you use those tools to gain insight and meaning into your applications is what we're doing with this kind of using it in machine learning and engineering and all that. So for example, like I said, matrices could be just any rectangular array of numbers. One way to think of them as to give meaning to our everyday world is to think of them representing pictures. For example, if you look at this picture, it has a certain it is composed of a number of pixels, as you already know. And for example, this particular picture has 28 pixels, and it's a 28 by 28 pixel picture. And each pixel has a value. 0 corresponds to black, whereas 255 here corresponds to totally white. And anything in between corresponds to something in the grayscale. And this picture can be totally, or it can be represented by this matrix of numbers. And if you actually look at it, you do see the correspondence, like the places where the white line traces the figure of 2 can be seen here. And the more white it is, the more higher the number it is. And this is actually a very fundamental way how we use matrices for computer, image processing and computer vision applications. Matrices can also be thought of as linear transformers. So how can you transform or rotate or linearly transform any coordinate system into another coordinate system? For example, this matrix, which is -2, 0, 0, -2, transforms this coordinate system into this. Let's say this red square gets transformed into this red square, which is now the bottom of the origin to the left bottom of the origin. The yellow one also gets transformed. Similarly, the dimensions of the square, which were 1 by 1, is now increased to 2 by 2. The image can be thought of having rotated counterclockwise by pi, by 180 degrees, or is it more than 180 degrees? Yeah, by 180 degrees, yeah. So stuff like that. So you can think of it as a transformer that takes a coordinate system and converts it to another coordinate system. It can also be used to solve a linear system of equations, which I think this is usually how most of us are introduced to linear algebra or matrices and vectors in general. So you have this system of equations. So for example, x minus y equals -1, 3x plus y equals 9. Find the x and y that fulfills both of these equations. So this can be represented as this matrix. So for example, 1x minus 1y gives you 1 and -1. 3x plus 1y gives you 3 and 1. -1 and 9 go here, and xy stay here. So if you follow the rules of matrix multiplication, which we'll go into later, but basically x minus y equals -1, and so on and so forth. So basically, what we can think of is find the vector xy that, when it is transformed by this matrix, gives you the vector -1, 9. And this corresponds to, in the geometric space, in the geometric, not geometric space, the geometric interpretation, as the point that lies in the intersection of these two lines. The reason we do it in a matrix form is because it is very computationally efficient. We have lots of algorithms, and the architecture and the computers that we use are very well designed or very well optimized for matrix manipulation kind of operations. So it's very easy to solve, or very fast to solve, these kinds of equations. Another interesting way we can use matrices is by representing graphs. For example, this is something called a directed graph. You have different vertices, 1, 2, 3, 4, and edges that connect them. And these edges may have some weights in them, but for example, for now we're just looking at how each vertex is connected to each edge. So how we can represent this graph in this matrix is that, for example, from 1, what is connected to 1? So for example, from 1, does it go to 1 again? Is there a loop back? No. So it's 0. There is 1 connected to 2? No. Is 1 connected to 3? Yes. So from 1 to 3, we give it a value of just 1. 1 basically means there is a connection. Is 1 connected to 4? No. So there's a 0. Similarly, there's nothing connected from 2 to any of the other vertices, so everything else is 0, so on and so forth. So creating a matrix like this helps us, and once we have this matrix, if we perform, for example, operations on it, we can figure out many insightful, we can develop many insightful intuitions about what these connections represent. For example, if you were to square this matrix, the values on this, well, not this matrix, but for an undirected graph, if you were to square it, it would give you the number of paths you'd have to take to go from one vertex to another. Another very, very interesting and useful and widely used application of matrices is for dimensionality reduction. We will go slightly into this during the Eigen Decomposition or the Eigenvectors, but this is mainly used as principal component analysis, where basically what we do is, for example, if we look at the picture that we looked earlier, which is a 28 by 28 pixel, you can think of it as, so this is only for this particular picture. Now, if we take a number of different pictures with all 28 by 28 and flatten them into 784 and put them into principal component analysis on that matrix, we can somehow compress all that information into just 10 numbers, or I mean into however number of numbers you want. If you do it into 184 numbers, all that information can be represented within 184 numbers. And once you decompress that, you can kind of recover the original image from this. So think of it as compressing all the information here that was originally in 784 numbers and decompressing it back, but using only 184 numbers. This is kind of like how you would take a raw picture in your phone and compress it in your JPEG, in a JPEG or GIF form. And if you use even less numbers to compress it, of course there is some reduction in quality, but still some, you can still get some meaningful information out of it. This is called principal component analysis, and this uses matrix, let's say algorithm, or not algorithm, but a matrix operation, something called singular value decomposition. So let's now go into what vectors and matrices are. So vectors are simply, like I said earlier, it's this ordered list of numbers, and we probably already know that it has a magnitude and directions. They represent quantities with some sort of magnitude and direction. So, for example, distance and displacement. Distance is not a vector, whereas displacement is a vector. And they follow rules of vector addition and vector multiplication. For a really good introduction into what vectors are and linear algebra in general, I really recommend you go to 3 Blue 1 Brown channel. I'm pretty sure most of you already know this, but just in case, it is run by a mathematician named Brent Sanderson. He has very beautiful animations and very intuitive and easy to follow explanations for linear algebra. If you follow the link, you'll go to this YouTube channel, and he has an entire playlist called The Essence of Linear Algebra, which I highly recommend anyone, not only machine learning, but anyone who needs linear algebra, wants to learn linear algebra, to go through it. So some just notations. So a vector is usually, there's an arrow on top, there's a letter that represents vector, and this is something you will see a lot, which basically means this vector is n-dimensional. It exists in an n-dimensional space, which basically is one way of saying it has n different entries in its in it. So n different numbers make up this vector u, and because putting this arrow all the time is a little bit inconvenient, sometimes people just bold it, and that is called, that's just vector. A vector and sets are different, although vector and sets may have similar components. The reality represented by a vector and the reality represented by a set is very different. One main important point is, in a set, the order of the elements doesn't matter, whereas in a vector, the order really matters. So if you were to change u2 and u1 here, it would represent a completely different vector. However, if you were to change u2 and u1 here, I mean interchange their positions, it will not really matter that much, or it is equivalent to the original one. There is something called a transpose of a vector, which is basically putting it on its side. So a transpose of this vector u would be to take this vector to transpose it, which make it from a column vector to a row vector. And of course, an important point here is that the transpose of a vector is not necessarily equal to the column vector, to the original vector. Yeah. Vector addition, very simple. You just add the corresponding entries of a vector. For example, we have a vector 1, 3 and another vector 2, minus 4. And if you want to add these two, we add the first components together. So 1 plus 2 will give you 3, and 3 plus minus 4 will give you minus 1. Negating vectors is basically the same thing. It's like just putting minus inside this column. And so I think we all already know this, and we already have this some sort of geometric intuition behind this. So for example, if this 1, 3 vector is u, so 1 and 3, and 2 minus 4 would be 2 and minus 4. Oh, sorry, 2 and minus 4 would be here. That's the v vector. So adding these two vectors will give you u plus v, which can be thought of as transposing this vector, not transposing, but let's say taking this vector and putting at the beginning of the the head of vector v, and whatever resultant vector you get is the addition of them. We also looked, I'm pretty sure at some point in your mathematical course you had to do it as a parallelogram. They basically mean the same. But why is this a valid addition technique? Why do we add these two components together and these two components together? Why couldn't we add 1 and -4 and 2 and 3 and get some result here? Why doesn't that make sense? That is a question that I would like you to ask. These are so basically in this presentation, these are the questions that I will not particularly answer, but inspire you to ask why we are doing things this way. So, for example, if you were to say, oh, it's obvious that if you just add these two things, we get this, and it makes complete sense, then I would counter question you with, then why can't we do this with polar coordinates? For example, the same vector 3, 4, 3 and 4 can be represented by the polar coordinate with magnitude of 5 and the angle of 53.1 degrees. So if we have two numbers, we just put them in one array, and then of course we can say that's a vector. But this vector is not the same as this vector. They represent completely different things. So why cannot we use polar coordinates as vector to represent lines or points in 2D space? Well, the answer is because they don't follow the rules of vector addition and multiplication. Especially if you add two polar coordinates, doesn't mean you will get the resulting coordinate through that process. Scaling a vector is simply multiplying a vector by a scalar. So you stretch and squish a vector, you only change its length, so not its direction. When we say the direction, we mean the overall direction. So if you multiply by a negative number, it will flip on the origin, so it will point in the opposite direction, but the main linear direction is the same. As you already know, a vector can be, if you multiply a vector with a scalar k, it's just 3 into, you will just multiply each of its components by that scalar. In fact, the word scalar comes from the word scaling. You can think of it that way, or the other way around. Scaling comes from the word scalar. So now we go to what we call span of vectors. So this might be something a bit new, or I don't know, depending upon what courses you've taken. So if you assume S is a set of vectors, so you have a number of vectors, let's say U and V or V and W or whatever. These set of vectors can be thought of as a vector space. So, and the span is basically all the combinations of the vectors in this vector space or this vector set. If you have a vector V and W and you add them and scale them in whatever way is possible, you can go to any point in this 2D space. So it can span the entire two-dimensional point. And that is why we call it the span of vectors. So all the different points all the different vectors, these two vectors can represent by their linear combination, which basically means by multiplying them by some scalar and then adding them together is called the span. However, sometimes if you have very special vectors like you see in the animation below, you can add and multiply these vectors as much as you want, but you will always be constrained within a single line. So this or a very small constrained space. So for example, the span of these two vectors is this single line only. It doesn't span the entire 2D space. So just because you have two vectors does not mean that you will be able to span the entire 2D space. That is something we should keep in mind. Like I said, so for example, these two vectors, even though they're not perpendicular to each other, can still span the entire 2D space. Of course, these two perpendicular ones also can span the entire 2D space. However, these two cannot. They can only span the entire line, the entire 1D space. Similarly for these two vectors. So given this concept of spanning, the span of vectors, we can say that then we have the concepts of linear dependent vectors and linearly dependent vectors and linearly independent vectors. So linearly dependent vectors are those vectors that can be represented as a linear combination of two other vectors. So for example, if vector u can be represented as a scaled and summed version of two vectors, let's say v and w, then u is linearly dependent upon v and w. However, if the vector u can never be represented as a linear combination of v and w, then it's a linearly independent vector. So if you go back to this slide, this vector, the magenta vector, can be thought to be linearly dependent upon v and w. Whereas in this animation, we can think of, let's say, w as being linearly dependent on v because it is simply a scaling of vector v. So when we have three vectors, we can span the 3D space. We could span the 3D space, but not always. So for example, if you have three vectors pointing in three different directions, let's say, you could basically take the entire cubic volume of this 3D space, and you can point to any of these points in the space. However, sometimes if one of those three vectors is linearly dependent upon the other two, then you would only span a plane in the 3D space. So even though you have three vectors that are all 3D, you would still only be able to represent all the vectors only in one plane, as you can see in this animation. So, and that brings us to the concept of the basis of a vector space. So the basis of a vector space is a set of linearly independent vectors that span the full vector space. So basically what that means is take some vectors that are linearly independent, so which means they don't you cannot get one vector from another, and if you can span the full vector space with those two vectors, then those vectors are called the basis of that vector space. A vector space can have several bases, so it's not unique. For example, like we talked about, these two vectors are both basis vectors for 2D vector space. And all bases have the same number of dimensions, basically the dimension of the vector space. So if it's a 2D vector that spans, if 2D basis vectors are spanning the entire 2D space, then their entries will have two numbers in them, basically. It's just a mathematical way of saying this. So now we go to matrices. Matrices can be thought of in two ways when you come to machine learning. First of all, you can think them as a collection of vectors. This representation is not correct in the sense you don't put vector signs here in that sense. So basically what I'm trying to show here is it contains the components of vector u, this contains the components of vector v, this contains the components of vector w. So you can think of them as a collection of vectors, and I will say why this is important later. Or matrices can also be thought of as a function that transforms vectors. So for example, if you have an input vector here that gives you an output vector here, the matrix that does this is called, the function that does this can be represented by a matrix. Like we saw earlier in one of our examples, the matrix that transforms this particular, let's say, square into this can be thought of as a matrix which is represented by -2, 0 and 0, -2. So the rules of matrix are very similar to vectors. You just add the corresponding entries together. 1 plus 6 gives you 7, 0 plus 2 gives you 2, so on and so forth. But the more interesting part is the vector products. So we have three different types of vector products. Most of us are very familiar with the inner product, but there are also two other called the Hadamard product and the outer product, which I actually cannot. I don't really have a good example for an intuitive explanation, but I'm just saying this just so that you know. So the element-wise multiplication is called the Hadamard product, where basically you multiply each entry with another corresponding entry. So A1 with B1, A2 by B2, A1 B1, A2 B2. This is especially useful when we do something called convolution in image processing. So you have a image and you have a kernel and you want to multiply the image with the kernel, which I think in the previous presentation somebody must have already talked about this. So that is basically element-wise multiplication is the Hadamard product. Then we have the outer product, which is basically you take one vector and scale each of its scale that vector with the entries of the other vector. So for example, this is from Wikipedia. I was lazy to actually type this out because it seemed pretty convenient, very well defined. So if you have a vector u, you have u1, u2 all the way to um, and you have a vector v, v1, v2, vn. So you take your vector u and multiply it by the first, you scale it by the first entry of vector v. So v1 into u1, v1 into u2, so on and so forth, v1 into um, you get the first column of this of the outer product. Then you take the second entry of v and scale the vector u with it, and you get this. You get the second column of the outer product, and so on and so forth. This is a useful mathematical tool, but I don't have a good visualization or intuitive visualization for this. If you do, please feel free to share. I would also be very interested in knowing about this. So now we come to the dot product. The dot product is also a very element-wise multiplication, but with a summation. This you already know. So if we have vectors x and y, we multiply them one by one, this following the rules of matrix multiplication, and we get one number. So the dot product gives you a particular, the dot product gives you a scalar as a result and not a vector. You have to follow the rules of this dimensions, and that's basically it. The geometric interpretation that we're all mostly familiar with is simply how much these two vectors overlap with each other. And this is a very interesting way of looking at it. For example, when I was doing my grade 9, 10 mathematics class, we used this as a way to find the angle between two vectors. So we would say cos theta equals to the dot product of x and y divided by the magnitudes of x and y. It's equivalent mathematical implication, or the other way of saying that can be said that x and y, the dot product of x and y is maximized when x and y are parallel to each other. So if x and y are pointing in the same direction, then you get the largest magnitude possible of their if you multiply their magnitudes together. And oh, sorry, this should be 0 when theta is 0, not pi by 2. And when x and y are completely perpendicular to each other, then they have no effect on each other basically. So their dot product is 0. That is one intuition that you can look into it. There is a very good intuitive video on this, again by Grant Sanderson in 3 Blue and 1 Brown, which I really recommend you watch. It gives you the intuition behind why you actually do this kind of multiplication. Why are we actually multiplying these and then adding them? I mean, we all know it's a rule, but like, why really? And if you want to know the answer to that, this YouTube video is a very good way to start. So the reason I bring this up on that when x and y, x dot y, or the dot product of x and y is maximized when x and y are parallel, is because it is very, it gives you a very good intuition when we use dot products for neural networks. So I hope most of you already know what neural networks are to some degree. So I will not go too much into detail here, but think of it as you have a couple of weights, a couple of inputs here. So 1, x1, x2, xm, all of that. So you can think of this as a vector. and then each entry of this vector needs to be, or each of these inputs has to be weighted by some scalar. So one has to be multiplied by theta naught, x1 has to be multiplied by theta 1, and so on and so forth. And once you multiply each of these inputs by some weights, then you add them together, and then you perform some nonlinear function on it, like tan h or sigmoid or ReLU or whatever you call it, and whatever you get the output is the output of that neuron. So this is basically the basic neuron that most of us are familiar with. Why I'm talking about this right now is because if you take the inputs as a vector from x1 to xn and the weights as w1 to wn, the multiplication of all of these, of each input with its corresponding weight and their addition in the neuron can be thought of as a vector product of the weights with the inputs. So weights w1, w2, wn with the dot product of x1 to xn will give you some value, and this will be given to y to the nonlinear function, and some output will be given. But why are we really doing this? What is this dot product of weights and dot product of inputs? What does it really mean? What is the implication behind this? You can think of it as, if the input, if the vector that is represented by the input is very close in direction, now whatever that direction means, but is very close or is parallel to the vector that is represented by the weights, then you get a high output. The output is large, because as we said earlier, x dot y is maximized when x and y are parallel to each other. Now it's very easy to grasp this when it is in 2-dimensional, but when you have like n dimension by n dimension, then it is not very easy to visualize it. But what you can think of it is that in whatever space these vectors and weights exist, if they are similar to each other, if they have some similarity, there is some way you can say x vector is very similar to w vector. And if you take the dot products, they have the output will be very large. So the larger the output, the more similar x vector is to the weight vector. So what is the weight vector really then? Then you can think of the weight vector as some sort of feature. So for example, this is just for intuitive purposes, don't take it too seriously, but let's assume the weight vector represents the number of eyes in a picture, and the x vector represents the picture itself, whatever picture you give. So if you have a picture of a chair, and then you dot product it with the picture of with the feature vector that contains 2 eyes, you would get very low output, or you should get. We would ideally want the output, the dot product, to be 0 or very low, because a chair has no features that pertain to eyes. However, if you were to give it a picture of a person or a dog or a cat, then multiplying that with that particular weight vector, or what we call a feature vector, because the eyes are some sort of features that you are looking for in the image, if you multiply them together, we would like the dot product to be large, to be of high magnitude. Basically, what we're saying is there's a large activation of that neuron. That neuron fires when it sees a picture with 2 eyes. So this is kind of a very simplistic, inaccurate, but simplistic, intuitive idea how you can think of dot products as driving the actual neural networks inside. Of course, there's a lot more going on inside neural networks, but this is one way you can start. Now we go to matrix multiplication, which is one of the things that has puzzled me for a very long time, which had puzzled me for a very long time. In fact, I remember after I graduated from university, and I think even 2 years after that, I had a conversation with one of my friends, and I was telling him, we all know this matrix multiplication, and we know that we should multiply with 2 by 3 and 1 by 1, add them and get this, but why are we actually doing this? Like, what is what is the logic behind it? It seems to make sense, that's fine, but why? Why did anyone create this kind of multiplication? And it took me another 1-2 years before I actually figured out why we do this. So we all know matrix multiplication: 2 into 3, 1 into 1, you add them, get 7. So basically the dot product of 2 and 1 with 3 and 1. And then 1 and 3 and 3 and 1, you get this. But I started looking into this this lecture video by Gilbert Strang in MIT OpenCourseware, which actually Sandis told me to watch. And in the very first of his lectures, he says, look, you can think of this matrix multiplication as scaling the first column of this matrix by 3 and scaling the second column of this matrix by 1. And if you actually do it, the answer comes out to be same. So if you just split this matrix into 2, 2, 1 and 1, 3, and you scale each of them by the entries in this vector, you actually get the same result, and it's actually consistent. It works for all matrices and vectors. So that's a very neat trick. And but I mean, it's fine. That's a really nice connection. But what does it really mean then? What's really happening there? So to do that, let's look at the same matrix 2, 1, 1, 3, and multiply it by a much simpler vector 1, 0. So we all know 1, 0 is this unit vector in the x direction. That's a very intuitive 2D representation of this. So if you multiply this matrix with this vector, we get this vector, which is 2, 1. Now remember earlier we talked about matrices as linear transformers, or functions that transform vectors from one to another. So if you take I and multiply it by, if you transform the vector I with this matrix, you end up with this vector 2, 1. So this I vector transforms to 2, 1 because of this matrix. And if you look at it, if you look at the actual multiplication going on, what you're basically getting for answer is only the first column of the matrix, if you look at it. So if we cover everything up and just look at this matrix, what it is telling us is that 2, 1 is the vector that 1, 0 would be transformed to by this matrix. Okay, let's see if maybe that's a bit confusing. Now let's go to the other vector. For example, 0, 1. If you multiply these two together, you get the second column of this matrix. Whatever this column was, it doesn't matter, but the second column of the matrix is the answer when you multiply it by the j vector, which is true. So the I vector got transformed to this vector here, whereas the j vector got transformed to this vector here. Okay, that's fine. So how does it help us then? It helps us by getting the idea that with this matrix basically tells us where the I vector is transformed to and where the j vector is transformed to. Okay, fine. That's pretty cool, but then why is it useful? It's useful because we already know that any vector can be represented by a scaled summation of the I and j vector, because they are, like we said earlier, they are the basis of the 2D vector space. So for example, the multiplication of 2, 1 and 1, 3 with another some random vector 3, 1, we can represent this random vector 3, 1 as 3 into I vector plus 1 into j vector, which makes sense. And we already saw that when you multiply this matrix, with the I vector, you only need to take the first column, so we get 2, 1. And if you multiply this matrix with the j vector, which is 0, 1, you only need this column, so 1, 3. So, and if you just scale them you already have these scaling factors here, you get them, you get the answer 7, 6. So what we basically did here is just a very easy way of, the short form of writing is this one. You take 3, multiply the first column, You take 1, multiply the second column, you get 7. You get the answer. So it's this particular very simple matrix multiplication that we all know, we already did 100 times, but it has very beautiful meaning and insights into the entirety of linear algebra. Basically, the matrix is saying, I know how to transform any. I mean, if you look at the matrix, you can say you know how to transform each of the I and j vectors. And because any vector in that 2D vector space can be represented by I and j, you can basically transform any vector in. You can basically know where any vector will be transformed to by this matrix. So I don't know if this made a lot of sense, but if you want a more better comprehensive explanation, please go to the YouTube link. Grant Anderson has a much more thorough and exhaustive explanation for this. So we looked at matrices as linear transformers of vectors. Now we go to the historical origins of matrices, which is basically matrices and linear equations. So matrices were originally developed to I wouldn't say develop to solve linear equations, but the linear equations, solving of linear equations somehow inspired people to develop mathematics. So I don't know if you've done this in school, but basically any matrix, any system of linear equations can be represented with a matrix vector multiplication. So 2x plus 5y plus 3z, and all of this, 2 goes here, 5 goes here, 3 goes here. So the coefficients of these linear matrices can be put in a matrix, the unknowns can be put in a vector, and the constants can be put in another vector. So this is a valid representation of this system of equations, which can be represented as a matrix into a vector, giving another vector. The x vector is the unknown vector, and the v is let's say, the constant vector. One way to represent this is to think of, find a vector x, this vector, such that when transformed by the matrix A, it goes and lands on vector v. And while that might seem like, okay, why are we doing it this way? We can just solve for them. This gives you a very intuitive way of looking at how these transformations are happening, whether this system of linear equations can actually be solved in the first place or not, whether it has unique solutions or not. These kinds of things can be not derived, but you can check for these kinds of conditions if you put them in this matrix form. But one of the main reasons why we use it in matrix form is because it's very easy to compute. When you put these numbers in a matrix form and feed them to a computer, you can parallelize their computation much faster, and get results much faster. I will actually not go into how we're going to do this. There's a whole lot of literature and videos and books that go into how you can solve linear equations using matrices. Basically, they start with something called Gaussian elimination, then there's the LU decomposition, and so on and so forth. While they are interesting in their own regard and they help in accelerating these computations in computers, I could not find a very intuitive way to show what's really happening here. So I will leave that for now. And there are still a lot more details underneath here where you have to talk about the column space. What do you mean by a rank of a matrix? What do you mean by a null space and orthogonal vectors and all of that? These are all just names for very special kinds of quantities and vectors and matrices. So I didn't want to go all of that. I didn't want to go into all of that right now, because in 1.5 hours I didn't want to cram too much information. Rather, I wanted this to be more like a relaxed presentation where you kind of get the intuition behind the matrices and vectors. So yeah, please go to the links that I will give at the end of the slide to go more into how you can solve linear equations using matrices. But the most important thing, or the more fundamental thing I would like you to think of, is that when you're solving these equations, think of them as finding this kind of vector that actually is transformed to the resulting vector. So you're trying to find the vector x that transforms to vector v. Gilbert Strang's lecture videos, especially the first few ones, I think 1 to 3, are a very good way to get started. So now we go to what we call eigenvectors and eigenvalues. And again, this was one topic that really, I could not grasp this topic when I was in my bachelor's, or because I knew how to compute them, I just didn't know what they meant. And once I had to use eigenvectors and eigenvalues and really develop intuition, then I found out that they're actually a very beautiful, very insightful way of representing matrices. So I took this from this slide, from this PDF from MIT also. So basically, as we said, matrices transform vectors. So they can rotate the vectors, they can scale the vectors, they can kind of take them to another place in general. However, sometimes some matrices, for a particular matrix, there are some vectors that when you transform them, they are only scaled. So for example, if you take this x vector and you apply this transformation called A, which is a matrix A, the resulting vector you get is simply a scaled version of x. So it's lambda into x. Lambda is a scalar number, and this scalar number is called an eigenvalue. So what basically this, by knowing this particular vector that is only scaled, you can tell a lot about the matrix. And I will go more into this detail in an example later on. But these eigenvalues tell how much this particular vector is scaled, and the eigenvector is the vector that only changes in magnitude when transformed by the matrix A. So for example, again, I took this GIF shamelessly from 3 Blue 1 Brown videos. If you look at this particular matrix 3 0 1 2, if you okay, let's wait for it to restart. You can see that this vector, the green vector, always is only scaled. There is no change in direction. So one way of saying that is it remains on its own span. Whatever the resultant vector is simply a linear combination of the original vector, which is, since it's just one vector, you can only multiply it. So it remains on the same span. The same thing can be said for the yellow vector. As you can see, it stays on this line, and only the magnitude changes, the direction doesn't change. However, the red vector, there is a change in direction. So if you wait for the animation to restart, the red vector is actually the j vector that changes to this another vector. So there is a change in magnitude as well as direction. So the red vector is not an eigenvector, whereas the green and the yellow vectors are the eigenvectors. So eigenvector is the vector that only scales after transformation, and the eigenvalue is the amount by which the eigenvector scales or is stretched or squished. So for this particular transformation, or 3 0 1 2, the matrix, the transformation represented by this matrix 3 0 1 2, the green vector, the vector that is represented by the green line here is stretched by 3, so that its eigenvalue is 3, and the eigenvector is simply the vector I here. Similarly, usually eigenvectors are represented in a normalized form such that their magnitude is always 1. And similarly, for the yellow vector, it is stretched by 2, so its eigenvalue is also 2. and the vector is represented by this line with a unit with a magnitude of 1. So that's all. That's just basically it. That's what eigenvectors and eigenvalues mean. There is quite, let's say, there is a mathematical. You need some mathematical rigor to calculate the eigenvectors and eigenvalues. I wouldn't say rigor. You just need to do some calculations to do it. It's not very simple. You can't just look at a matrix and say, okay, this is the eigenvector and this is the eigenvalue. Although sometimes you can, but in general you can't. But the what you're really doing with all that calculation, with all that solving of equations and all that, is finding a vector that only scales when you use the transformation and the value by which it scales. So this is eigenvector and eigenvalue thing.
So the question is, why can eigenvector never be 0?
Why can eigenvector never be 0?
Are you talking about eigenvector or eigenvalue? Yeah. So the question is, why 0 vector is never an eigenvector, or the eigenvector can never be a 0 vector?
Why can't an eigenvector be a 0 vector?
Yeah.
Well, I guess, I mean, you could technically say, you could say it's a eigenvector because well, 0 vector is a very special vector. You could scale it, you could you wouldn't really be able to say whether its direction changes or not. Well, I guess the honest answer would be I don't have a good answer to that right now, other than just showing it to you by calculation. But if you look at it in,
I think
maybe Sandesh can.
Yeah. So basically, what you want is, other than for the tautological reasons, what you want is eigenvector to do some sort of. I want them to do some job for us. For example, I want them to span some space. We want them to cover some space. We want to make them some basis so that we can compute vectors and so on. But if you include a 0 vector, no matter what you do to it, it will never be able to span any vector space, because no matter how much you multiply it or add it to something else, it would always be 0, right? So you cannot really achieve anything with the 0 vector. So I think when they started with the definition, they just excluded it so that it won't give you a lot of pain. So I guess that's the reason.
Yeah, maybe there's a utilitarian reason behind why they don't use 0 vectors as eigenvectors. There might be a more mathematical formal proof behind it, but if you go with the definitions that I just gave, that eigenvectors are vectors that only scale and the amount by which they scale is 0, then obviously with this definition you could include the 0 vector as eigenvectors and eigenvectors. Yeah. Okay, so let me just go to the rest of the slides. This again is not my original work, of course. If you really want to go properly into all of it and really understand what's really happening, please watch this YouTube video. In fact, the following slides are simply screenshots of that video. So this is simply to motivate why we are doing eigenvectors and eigenvalues. So maybe this will kind of answer the why we can't have 0 eigenvectors also. So suppose in a 2D, we are now in a 2D space and we have some n data points, right? Although the original author goes like m dimensional space. Let's just assume it's a 2D space and you have some number of points here. And we would like to know how these points are kind of clustered together. The reason behind why we want to know that particular line along which these are clustered is, well, there are many different reasons, but one reason could be to extrapolate. So while we know the values for the y values for these x values, what would be the y values for, let's say, this x value over here, maybe somewhere? I mean, we as humans can look at it and say, oh, there's a line here, and somewhere over here there should be a point. But mathematically, how would you say that? So maybe you'd like to know which line kind of best represents, which line best fits between these points. Another way could be what we talked earlier about compressing the data. So for example, you have, I don't know how many, 1, 2, 3, 4, 5, probably 10, 20 points here. And let's say each of these points contains two numbers, the x coordinate and the y coordinate. So if you assume there were 20 points here, we would need 40 numbers to kind of represent all of this data. But if somehow we could find a line here, which is basically y equals to mx plus c, if you just knew the slope and well, in this case, just the slope, I guess, and the c, which is the y-intercept of the line, you could represent all of this data with just two numbers, the slope and the intercept. So do you see, like, you compressed 40 numbers into two, and you still didn't lose too much of data, I mean, too much of information. You could still kind of figure out what this shape looks like, or where this data is going to. And so that's a very interesting unsolved, I would say, problem in machine learning, in mathematics in general. When I mean unsolved, it has a different implication, but basically if you can somehow squish a large dimensional data into a very small number of dimensions, you could save a lot of memory. So since I'm from computer architecture, these are the things I need to think about, like how can you save things on memory. So if you have a 5 GB image, how can you represent it in 256 KBs in a way that you still get some meaning out of the image. Or sometimes you might need this sometimes when you need to transfer data across, let's say, your mobile phones. Like you can have a 4K video playing somewhere, but then to watch on your mobile phone, you only need, let's say, 1080 HD. How do you compress all of that while keeping the semantic meaning, but losing some unnecessary information, compressing it? So that is why this kind of line, or in a more mathematical term, why this subspace is required, a lower dimensional subspace. So let's take these data points and represent as a matrix. So in this case, the author used them as simply like students and their scores in math and history or whatever. So you represent the data points into M by N matrix, and then you multiply the matrix with its own transpose. So remember, we talked about transpose earlier. The effect of multiplying the matrix with its own transpose is that it converts any non-square matrix into a square matrix. So an M by N matrix, when multiplied by its transpose, becomes an M by M matrix. And there's also a scaling factor of n minus 1. This is basically you're kind of centering the data so that it fits kind of nicely on the 2D space. Of course, there's a lot more going on there. That's why it's technically called a sample covariance matrix. But for now, that is not very important. We're just looking at how we can use eigenvalues. So you take this matrix, and then you find its eigenvectors. So the vectors basically, so please keep in mind now that this matrix now does not really correspond to a linear transformation of any of these vectors. It does, but not in the way we just talked earlier. Sorry, not this matrix, but the A into A transpose. That the matrix, the A into A transpose matrix, or the covariance matrix, now represents how these data exist in this m-dimensional space. It's a representation of all the information that is captured by the data. And if you do the Eigen Decomposition, which basically means decomposing that matrix into its eigenvectors and using those scale vector and finding their scale factors, what you actually find is the eigenvectors represent the the principal, well, she calls it the principal direction of the data, which basically is the line that best corresponds to how the data can be clustered together. But I, of course, didn't go like rigorously and formally into it, but usually if you have a two-dimensional matrix, you have two eigenvectors, and they all have their eigenvalues, and they can be real and imaginary and all of that. So in this case, for example, this eigenvector E1 is the eigenvector E1 has the scale factor of 57, which basically means the eigenvalue is 57, and whereas the eigenvector E2 has a scale factor of 3. And somehow, if you look at all the maths and try to get intuition from it, what you find out is that the one with the higher scaling factor gives this principal direction of the data, or gives the line around which the data is clustered. And this is one way you can kind of figure out how this data is arranged, or what insight you can get into this data. Maybe this line is meaningful to someone who is doing data analytics. Now, for example, this was simply like students and math and history, but for example, if you could think of it as the movies you have watched and the different users here, something maybe Netflix would have on its data bank. And if you were to find this eigenvector, it would help you in recommending what next movie you would want to watch. Think of it something like that. Of course, it's not right to just summarize it in this way, but this is a direction you can look into. So basically, the eigenvectors kind of represent the matrix in the most condensed form. They represent the essence of the matrix, eigenvectors and their corresponding eigenvalues. In fact, they become very useful when you want to have non-linear functions on matrices. So if you have some matrix and you want to, let's say, find the logarithm of the matrix, it is not as simple as finding the logarithm of each of the elements. You actually need to kind of decompose it into its eigenvalues, and then you find the logarithm of the diagonal elements of the diagonal matrix. So, and there's a procedure behind it. I haven't gone into it, but that is where eigenvectors and eigenvalues actually shine, let's say. So I will stop for now. I think I've been talking for almost 1 hour, 15 minutes. But again, like I said, this is simply a door to linear algebra. Please do not take this as a complete formal definition, because I haven't gone into the definitions properly. I've skipped out a lot of actually very fundamental concepts of linear algebra. But if you are interested, and I hope my talk got you interested in linear algebra, gave you some deeper insights, these links are a good place to start. Nowadays, the internet, the YouTube, Wikipedia, all of that, you have so much information, you get overwhelmed. So starting with the OpenCourseWare, where you can get a thorough, like the entire linear algebra course. Then you have the YouTube channel by Grant Sanderson, which gives you a very overview and very deep insights into it. So I would start with the YouTube channel here and then go into the courseware here. And this is one of the references that I use for the last, the clustering of the data and the eigenvectors. And this blog post gives you kind of like a summary of what Grant Sanderson says. So it's a good place to start. I didn't put too much information here, not to overwhelm you, but if you go on the internet nowadays, you can find anything else. So with this, I will stop my presentation. If you have any questions or anything in the next 5 minutes, I could talk about them. Thank you very much for your time, and I hope you enjoyed the talk.